Hi, everyone. Thank you for joining me. This is Ch13, and today we're covering Chapter 13, Inferential Statistics. So first of all, let's just recap what we talked about with regards to descriptive statistics. Remember, in terms of measures of central tendency, we have three types. So let's review mean. Mean, remember, is the arithmetic average. In other words, we take the sum of all the scores and then divide it by the number of scores. The pro to the means are that it's the only measure of central tendency that uses every single piece of numeric information in the distribution. And when drawing different samples from the same population, what you see is that the mean actually fluctuates much less than the median and the mode. The con for this is that it can't be used for qualitative data. So in other words, you cannot use it for nominal or ordinal data, and it is very sensitive to outliers. The mean, the median is the midpoint. So with the midpoint, remember, you order your data and you find the middle point. Either it's literally the middle in an odd numbered set, and in an even numbered set, you take the average of the middle two numbers. The pro to the midpoint or to the median is that it's not as sensitive to outliers as the mean is. And this is why real estate agents like to use the median instead of the mean in terms of the cost of houses. So a few outliers will not affect the median. And when you draw samples from the same population, it's going to fluctuate less than the mode, but more than the mean. Similar to the mean, you cannot use this for qualitative data. So it cannot be used for nominal or ordinal data. And it doesn't use all the information in the distribution because it's only looking at the midpoint. Mode is the only measure of central tendency that you can actually use it for every single type of data. So it's the only one that you can use for both qualitative and quantitative data. It's not affected by outliers at all. But if the guess is if you had to guess, a number, the mode is a good one because it is the most frequently occurring. What's the con? Well, it might actually not be a good representation of all the data that you have. And let's say, because you could have several of, one score. Let's say you have 3 zeros and everything else is, 1.3, 1.4, 1.5, and you go with the mode, then it's going to seem as if your whole data set was comprised of zeros. So that's not going to be representative. Also, when you draw samples from the same population, you're going to see a lot more fluctuation with the mode as compared to the median and the mean. So with descriptive statistics, the purpose is to describe, right? So we use that by offering up the measure of central tendency, which is mean, median, or mode, or we look at measures of variability. So measures of variability would be looking at range, which is, the highest and the lowest, variance, or the square root of variance, which is standard deviation. So here's an example where, if you had this little data set, 1, 2, 3, 3, and 4, the mean of it would be 2.6. The median, right, you have 3. And then the mode, you would have 3 as well. Now, if you change just one value and had 1, 2, 3, 3, and 400 instead of 4, you see how much the mean is actually affected by an outlier. So instead of 2.6, the mean becomes 81.8, which is not representative of the sample, actually. The median doesn't change and the mode doesn't change either. So this brings to mind the idea of sample size. If you have a large sample size, few outliers won't impact it. So here is an example of a very large sample. We have 500 ones, 250 twos, 500 threes, 500 fives, 500 sevens, 248 eights, 500 tens, and 2 400s, right? You have all of that comes up to 3,000 if you added it all up. And what this shows, if you take the mean, you have 1,634 divided by 3,000, which are the number of data sets, the mean is 5.34. So those values of 400, the two 400s, which are outliers, would not affect it. So that's why it is really important, if you are using quantitative data, that you have as large a sample size as possible. That way, a few outliers will not really affect it. All right, so let's go on to inferential statistics. When we talk about statistics, a lot of people don't actually know what we're referring to. So remember, when we're conducting research, the goal is that we want to collect data and come up with conclusions that will give us more information about the population in general, our population of interest. When we talk about statistics, the term actually is used to describe information about the sample, about the participants that we have gathered for our study. When we talk about the population in general, the terms that should be used are parameters. So statistics refer to the sample and parameters refer to the population. Sampling error is our assumption that we are going to have variability when we collect statistics. It's because it is actually really impossible to just randomly select participants, right, from a population and come up with the same values each time. So let's take a look at it. Here's an example of sampling error. Let's say we had 1,000 college students, and population parameters, right, are that the mean age is 21.3, the mean IQ is 112.5, and of this population, 56% of the population are female and 44% are male. Let's take sample one, and we just take 5 students: Bruce, Clark, Dinah, Shayera, and Wally. When we looked at them, the mean age was 19.8 years, the mean IQ was 104.6, and in that sample, we had 40% female and 60% male. As you can see, this does not match up with the population parameters. Now let's take sample 2, Artemis, McGann, Zatanna, Barbara, and Kaldur. So the mean age of this group is 20.4 years, the mean IQ is 114.2, and in this group, we had 80% female and 20% male. So if you are randomly selecting from a population, the likelihood that each sample that you're collecting has exactly the same matching data as the parameters is like almost zero. And so because of that, we assume that there will be sampling error. So why do we use inferential statistics? Well, the goal of sampling is, first of all, it's really very, very difficult, if not impossible, to get every single member of a population to participate in a study, right? So what we want to do is we want to collect a sample that represents the population as much as possible. But we know that the sample does not equal the population. Even by just looking at sampling error, we know it's not going to be the same. So inferential statistics helps us determine if the sample that we collect and the results we get from the sample will match what we would get if we sample the population over and over again. That's what the p-value helps us, determine, right? The p-value, when we see 0.095, so 95% chance that if we sampled the population over and over again, we would get similar results. That's what we're saying when we talk about these p-values or confidence intervals. We're talking about our confidence that the results we obtained through the sample will also be found in the general population. So inferential statistics, what it does is it helps to determine if the results of the sample, generalize is the word we like to use, external validity, if those results of the sample will generalize to the population. So the difference that we find between sample means, control group and experimental group, it should also be found if there's a true difference in the population plus random error. So even considering that random error can occur, we believe that the difference between the two groups, right, the one that got the intervention, the one that didn't, that would be found in the population as well. So inferential statistics helps us with inferences regarding whether there is a true difference in the population means using the sample data. So hypothesis testing. A hypothesis is our prediction of what will occur in the study. Hypotheses are supposed to be written in terms of the population parameters, and there are two general hypotheses. H sub 0 is also known as the null hypothesis. The null hypothesis is the same in every single study. The null hypothesis says that the population means are equal. In other words, any difference in the sample means are occurring because of chance or random error, and the treatment has no effect. This is a very conservative way for us as researchers to say, okay, we're going to assume that the intervention does not work, because it's easier to show that n equals 0, right? 0 equals 0, because there are multiple, there's only one way 0 can equal 0, but there are an infinite number of ways that something cannot equal 0. And so in terms of the hypothesis, we will always assume the null hypothesis, that there is no difference between our groups. The research hypothesis, H sub 1, is what we want to be supported. So the research hypothesis will be the population means are not equal, that the difference in the sample means are occurring because there really is a difference between the two, that the treatment does have an effect. That's what we want to see as researchers. So hypothesis testing is helping the researcher decide, are we going to reject or fail to reject, in other words, accept the null hypothesis? We want to reject the null hypothesis because rejecting the null hypothesis means that we are finding a difference, that our intervention is making a true difference, and that difference will be found in the population, that it's not just happening in our sample. Right, for example, let's say we had a study to see if hypnosis would actually help people in terms of their memory retention. So we have the hypnosis group, or HG, and then we have the control group, CG. The dependent variable is reading retention. The results we got is that HV, the mean number of words remembered was 22 with a standard deviation of 2. And for the control group, the mean was 15 with a standard deviation of 1.5. Now we need inferential statistics to help us determine, was the difference between 22 and 15 due to the independent variable of hypnosis, or did that occur because of random error? So let's take a look. Remember, null hypothesis, the population means are equal. In the research hypothesis, we're saying the population means are not equal. So how would we word that to specific studies? Well, the null hypothesis could be the population means of the control group is equal to the population mean of the hypnosis group. And the alternative hypothesis would be the population mean of the control group is not equal to the population mean of the hypnosis group. This reflects our belief that either there is a relationship in the population, meaning that we will see something going on because of hypnosis in the population, and the relationship in the sample reflects it, or there is no relationship in the population and the relationship in the sample reflects only sampling error. So if the null hypothesis is accepted, then that means there is no relationship between hypnosis and memory retention, and whatever difference we see is just because of sampling error. That's the interpretation. So H sub 0, or the null hypothesis, says the population means are equal, right? 0 equals 0. We test the null hypothesis, and then we decide whether or not we are going to reject it. If we reject the null hypothesis, then the inference is that the alternative hypothesis is correct, that hypnosis does make a difference in terms of memory retention. We only reject the null hypothesis when we find a very low probability, less than 5%, or chance that our result is due to random error. So the amount of probability that we're going to determine, the standard in psychology is 5%. So 95% confidence that any difference we find is due to our independent variable. That's really what that boils down to. So the very low probability, right, 100, remember probabilities are in terms of percentage, 100% minus 95, so less than 5%. That's what we're looking at. When we do hypothesis testing, it's really 4 steps, right? So the first is we assume the null hypothesis is true. We are assuming that our intervention doesn't work, that there is no relationship between the variables in the population. Step 2, this is where our research design is. We design our research, we conduct the research, and we collect the data. Step 2. Step 3, now we analyze data and we determine the likelihood, otherwise known as a probability, of whether any relationship we see is happening because null hypothesis is true or not. And then step 4, we come to a conclusion. If the sample relationship is highly unlikely, right, very low probability of it happening just by chance, then we reject the null hypothesis. If it is not extremely unlikely, in other words, there is a greater than 5% chance that it could happen, just randomly, then we will retain the null hypothesis. So there are 2 things that could happen. We could either make an assumption, make a conclusion that is correct. So here we have 2 dimensions. We have the researcher's decision, and then we have the reality of the population. So if the researcher's decision is true and the reality of the population is true as well, it's a correct decision. In other words, if the researcher's decision is that the intervention had an effect, and it really did have an effect, it's a correct decision. On the other hand, if the researcher says that there was no difference, and the truth in the population is that there was no difference, that is also a correct decision. But there are other errors that could occur. So type 1 error would be if the researcher decided that the groups were different and rejected the null, but in reality, the groups were not different, that it was actually by chance, we call that a type 1 error. If the researcher said, nope, the groups are not different, we're going to accept the null hypothesis, but in the population, there really is an effect, so that could be just a result of, too small of a sample, we call that a type 2 error. So let's go over that. So it's really important for you to distinguish between type 1 and type 2 errors. In a type 1 error, we reject the null, but the null is actually true. So in other words, we say the groups are different, but in reality, they aren't. So maybe in our sample, they seem to be different, but in the population, they are not different. There was no real effect of hypnosis. So this can happen if you get a large T or F value simply by chance, and otherwise known as random error. So the probability of making a type 1 error is also known as the alpha level. In psychology, our alpha level, our default alpha level is 0.05, a 5% chance of making a type 1 error. If we lower the alpha level, we have less chance of making a type 1 error, right? We have less chance of rejecting the null when the null is true, but we increase the probability of making a type 2 error. So let's look at what the type 2 error is. In a type 2 error, we accept the null. In other words, we say there's no problem. The intervention did not have an effect. But in reality, there is an effect. So in a type 2 error, right, we accept the null, but it's false. So what can cause this, right? Means that there's a non-significant result, but the difference is meaningful, first of all. So 3 things can cause a type 2 error. 1 is that the p-value is too low, right? Remember, if you put the p-value down, you decrease the chance of a type 1 error, but you increase the chance of a type 2 error. 2, sample size. If you have a small sample and it's a weak effect, then you might not be able to detect the difference, right? So small sample size decreases the likelihood of detecting a true difference. 3, effect size. If the effect size is small, you really need a large sample to see that effect in your group. And so if your effect size is small or weak and your sample size is too small, then your ability to actually detect that difference is severely hampered. So here's a fun slide that kind of summarizes that type 1 and type 2 error. So true positive is a doctor telling a pregnant woman she's pregnant. A true negative is telling a man he's not pregnant, right? Type 1 error would be a false positive. That is telling a man that he's pregnant. That's a false positive. And then a type 2 error, right, is telling a pregnant woman she's not pregnant. That's a false negative. So type 1 error is a false positive, meaning you think that there's a difference, but there really isn't. And then type 2 error is a false negative, meaning you think there is no impact, but there really is. So alpha level is also known as our significance level. As I mentioned before, in psychology, the standard is 0.05. So when we see a p-value that has that symbol, p is less than 0.05, what that translates to is that we have a 95% confidence in the reliability of our findings. That there's only a 5 in 100 chance. So in other words, if we repeated the study 100 times in the population, maybe 5% or less chance that the finding would be simply due to chance. That's what's saying. 5 in 100 chance that the finding is simply by accident, that it didn't really occur because of the intervention. So if something is very unlikely due to random error, then we can reject the null hypothesis. As I mentioned before, sample size is really important. The more observations or the larger sample you have, you increase the accuracy in the estimate of the true population value. So when I say sample size, it doesn't always mean more participants, it means more data points. So in a repeated measure study, you don't have as large a sample size, but you want to make sure you have a lot of data points for each participant, because it's really, that's what we're looking at, the number of data points. So the more data points you have, that is the more observations, and that increases your accuracy in terms of what's happening in your sample is also going to be found in the population. As the sample size increases, your confidence in the outcome, increases as well, in terms of that your outcome that you find in your sample will also be found in your population. So statistical significance. When we have a p-value of less than 0.05, we say that the differences are statistically significant. So what does that mean? Well, it means that we believe that our results are reliable, that they are consistent, right? Question we would answer is, would you get the same result if the study were conducted repeatedly? When we're talking about probability, we're imagining that the study is being done 100 times, randomly sampling from this population of interest, and that we believe the results, we are confident that the results will be found each time we get that sample. So the significance level, right? If we have a low p-value, it decreases the chance of a type 1 error, but it increases the chance of a type 2 error. So it decreases the chance of a false positive, but it increases the chance of a false negative. So a small sample size is going to decrease the likelihood of seeing the true difference. It's going to increase the chance that you're going to have a false negative and say, nope, it doesn't make a difference, when actually it does, right? I want to emphasize the difference between statistical significance and practical significance. So because the significance level, your results are really highly impacted by the sample size, you could have, if you have a huge sample size, which is now easy because of the internet and data mining, you could find something that is statistically significant, but not practically significant. So let's say that someone was able to do a study on the effects of caffeine and academic achievement, okay? And they're doing this on some kind of like online test. So they have 100,000 participants. And with this 100,000 participants, they find out that drinking 6 cups of coffee increases your score on a cognitive test by 2 points. Because you have 100,000 participants, that's going to be a statistically significant finding. If the 2 points are out of 100, right? Yes, it's statistically significant that consistently it raises 2 points out of 100, but is it practically significant? Would you advise, people to drink 6 cups of coffee to raise their, results by 2 points on a 100-point test? Probably not. So that's what I mean by you need to critically evaluate, even if something says it's statistically significant, is there practical significance to this finding as well? And now in this age of data mining, it's really important to consider that. So Cohen's d is the effect size, right? So what a Cohen's d does is it tells you the strength of a statistical relationship. This is what we mean by small effect, weak effect, right? The smaller the effect, the more participants or the more data points or observations you will need to demonstrate this small effect. This is where sample size becomes really important. So Cohen's d lets us know how effective, how strong is this difference in terms of standard deviation units. So this is really great when you're comparing results from different assessments, right? Because it's put in standard deviation units, the units don't matter. So a lot of times, if you're looking at a meta-analysis, it will be the effect of certain independent variables are going to be expressed in terms of Cohen's d. So why? Because in a meta-analysis, the researcher is looking at pre-existing studies, and oftentimes these different studies are using different operational definitions for self-esteem, for example. And what a meta-analysis does is they take those results, they put it in terms of Cohen's d because it's in standard deviation units, and then you can compare just how strong is self-esteem, is the, on academic achievement, for example. So even if you're looking at different studies that are using different assessments, because those results are translated into standard deviation units through the Cohen's d, now you can compare. So that's the whole purpose. So here's an example with Cohen's d. Study found that people ate more popcorn out of large containers than they did out of medium containers, right? How much more popcorn did people eat out of large containers? So let's see, in the medium container, they ate an average 58.9 grams, and with a standard deviation of 16.7. In a large container, they ate an average of 85.6 grams with a standard deviation of 19.8. So the formula for Cohen's d is you take the mean of one, the first population sample of interest and the mean of the second, and then you divide it by standard deviation. So we took the medium container mean, subtracted the large container mean of how much people ate, and you divided it by the pooled standard deviation, which is calculated combination of the first and second value. I would give you the pooled standard deviation. So the pooled standard deviation is 18.3. So you take negative 26.7 divided by 18.3, and it is negative 1.46. So what is the interpretation? Well, it turns out that comparatively speaking, right, when it's people eat 1.46 standard deviations less in a medium container than they did in the large container. That's the interpretation. All right, inferential statistics. So let's take a look at the different types of analysis. So remember when we looked at analysis, we said there were 3 ways we could do it. We can compare group percentages or frequency. We can compare group means, or we correlate individual scores. The whole purpose, remember, to the inferential statistics is we're using probability to test the null hypothesis. We want to determine if we are going to accept the null hypothesis, meaning we believe that our intervention has no difference, or we are going to reject the null hypothesis, meaning that we believe that there will be a difference. So when we have nominal data, nominal or ordinal data, which is considered qualitative, the only inferential statistic we can use is a chi-square. And there are three types of chi-square tests. There's goodness of fit, test of independence, or test of homogeneity. When we compare group percentages, it's important to know that we are looking at or counting occurrences. We're not actually measuring anything, right? So we're seeing how many times something occurs. So for nominal data, again, you can use chi-squared, and that symbol is how you know it's a chi-square analysis that you're doing. And for ordinal data, it would still be a chi-square. So when you have chi-square results, this is what it's going to look like. So that funny looking X with us, you know, the exponent, that tells you it came from a chi-square analysis. So as soon as you see that, you know it's a chi-square that was used. The 1 in parentheses is the degrees of freedom. So the way you calculate degrees of freedom is the number of groups minus 1. N equals 54 says how many observations or participants were included. So we know there are 54. And then you have the p-value. The p is less than 0.01. That indicates that the alpha level used by the researcher was 0.01, and that the value happened, you know, very, very low probability that it happened by chance. So in this situation, we would reject the null hypothesis. So here's an example of chi-squared results. You know, we have 4 different examples here. Chi-square test of independence was performed to examine the relation between gender and the ability to swim. The relation between these variables was significant. So there you see the chi-square, 1. So N equals 84 equals 8.9, P equals 0.0029. So either you're going to see the actual value of the P, or you're going to see kind of a generalized where it's less than another value. So it says women were more likely than men to be able to swim. So here, right in there, it actually states in this result what kind of analysis. In terms of the exam, I will not tell you what kind of analysis was performed. More likely, you would see the second one where it says the proportion of subjects who reported being depressed did not differ by marriage. Chi-square 1, N equals 104 equals 1.7, P is less than 0.05. So again, see the first example, the actual p-value is given, which is fine, p equals 0.0029. So here the researchers really wanted to emphasize how low the p-value was. So they were very confident that the difference they found, that women were more likely than men to be able to swim, did not happen by chance. In the second example, where they just say p is greater than 0.05, that means that they did not find, they would have to accept or fail to reject the null hypothesis, meaning there was no difference in terms of whether people were married or not. Depression was not affected by marital status. Third one, there is a significant relationship between 2 variables. Hipsters are more likely than non-hipsters to own an iPhone. Chi-squared 1, N equals 54, equals 6.7, P is less than 0.01. So here we did find a significant difference. So we're saying that being a hipster did make a difference. It was not by accident. That there was an association between that status of hipster or non-hipster and likelihood of owning an iPhone. And it says we had 54 people included. Chi-square test of independence showed there was no significant association between gender and chocolate. So you have chi-square 2, N equals 88, equals 2.1, P equals 0.35. So here they didn't use the greater than 0.05, they just gave you the p-value. So there are 2 ways it can be done. Either they give you the actual value, or they kind of generalize it to whether it's greater than or less than 0.05. So here's the same results in green. That's a type of analysis. That means it's chi-square. In yellow is the degrees of freedom, right? So it's number of groups minus 1. So in the first 3 examples, we only had 2 groups. So one was in the first group, all they looked at were women and men. In the second example, depressed or not depressed, or so married or not married. Those are the 2 groups. That's why you had 1 there. In the third example, hipster, non-hipster. In the fourth example, it seems that there were 3 groups, very likely male identified, female identified, and non-binary, right? So you have 3 groups there. In blue, that's your number of participants. So first one, there were 84, or number of observations. Second one, 104. Third one, 54. And last one, 88. And then what you see in gray are the p-values. So in the first example, they gave the actual value. In the second one, they just gave a general is greater than 0.05, which tells you it's not significant. In the third one, they just gave a general, it's less than 0.01, which means it's significant. And then in the fourth one, p equals 0.35, not significant. Okay, so in terms of comparing group means, you can only do that for quantitative variables, right? We could use the Cohen's d. And we often use, if we only have two or more groups, we would use a t-test. That's actually for 2 groups. So we have 3 types of t-tests. A one sample t-test means that you're actually comparing it to the population, but you just have the one sample group. Dependent samples t-tests, that happens when you have a repeated measure study, which is why it's called dependent samples. And then you have independent samples t-test, which would be for between group subjects, where you have completely different separate groups and that you're getting those results. So it would be control group and your experimental group, for example. So here are different examples for what a one sample t-test, independent t-test, and dependent t-test looks like. So you would read the results to interpret it. And from the results, you could actually determine what kind of t-test it was. So in the first one, comic book fans reported higher levels of stress, and it gives you the mean and standard deviation, than found in the population as a whole. So that's the key. When you see it's being compared to a population as a whole, that tells you it's a one sample t-test. And there's the T. So t-test would have the T to let you know it was a t-test analysis, right? 48, that's the degrees of freedom minus the number of groups. So if you have 2 groups, then the sample is 50, right? Then the N is 50 because you're adding 2 groups. And then there is your p-value, p equals 0.026. So that tells you that the difference was significant. Here's another example. Coffee drinkers spent more time awake, mean standard deviation, than the population norm. T, 28 equals 2.6. So 28 plus 2, there were 30, right? Because you have, or actually, sorry, 28 plus 1, because only one group, it's 29, and the other one is 49. And then you have the p-value is less than 0.05. Again, either way of reporting the p-value is acceptable. For independent samples t-test, let's take a look at what that looks like. So in the one sample t-test, again, you would see in the results that their comparison is with a population norm. In the independent samples t-test, let's take a look. The 25 participants who received the drug intervention, and they give mean and standard deviation again, compared to the 28 participants in the control group, right, mean 425, SD equals 31, demonstrated significantly better peak flow scores. So here, what you see there is T equals 51, right? Add 2 because you had 2 groups. So the number of participants is actually 53. And equals 2.1, P equals 0.04. And the fact that it is less than 0.05 tells you it was significant. So the larger the T value, the bigger the difference between the two. And the p-value gives you an indication of, how likely it occurred because of chance. So here, explicitly in the independent t-test results, it indicates how many groups are being compared. So you know it's not a one sample t-test. And then in the second example, there was no significant effect for sex. T38 equals 1.7, P equals 0.097. Despite women, and then you get the mean average for women and standard deviation, attaining higher scores than men. And there's the mean values for men. So in APA, you need to report the mean and standard deviation for each of the groups that you're comparing. So P equals 0.097, obviously that's higher than 0.005, and that's why it is a non-significant difference. So you would fail to reject the null hypothesis. Dependent samples t-test. So remember, this is repeated measures. So this could be a pre-test, post-test type of situation. The results from the pre-test, and there you have mean and standard deviation, and post-test, and then you have the mean and standard deviation of that group. Memory tasks indicate that the presence of caffeine in the bloodstream resulted in an improvement memory recall. So there's T, again, that's the analysis you have. You have 19. So remember, degrees of freedom is n minus number of groups. So there are two groups, it looks like, or two times it was replicated, so 21. And then you have P equals 0.006, which is very significant. It was a really good outcome. And then another way, in the last results, there was a significant increase in the volume of alcohol consumed in the week after the end of the semester, and there's the mean and standard deviation, compared to the week before the end of the semester. So there you see T, and then the 52 indicates there were, two groups there, sample size of 54, and you have P equals 0.001. So reading the results, you have to really pay close attention to all the details in it to give you an idea of what kind of analysis was conducted. So I could give you a result where it doesn't say what kind of analysis is conducted, and you should be able to read the results and tell me what kind of analysis. So even it's like one sample, independent samples, or dependent samples t-test. The T would indicate it's a t-test, and you just have to determine which kind of t-test it is. I might ask you how many participants or how many observations occurred. So degrees of freedom, remember, is n minus the number of groups, so you would calculate that. And I could ask you if it's significant or not. So those are things I might ask in terms of results. So this is kind of that breakdown that I just explained. Right, in terms of comparing group means, if we have more than two, then we would be looking at what we call analysis of variance, or ANOVA. So an ANOVA compares group means of two or more. It's also known as the F test. So when you see the results, you'll see from an ANOVA, instead of T, you're going to see an F. So remember, the funny looking X tells you it's chi-square. If it has T, then it tells you it's a t-test. And if it has F, then it tells you it's an ANOVA. So we often use ANOVAs for experiments. You have to post hoc experiment comparisons if you find a significant difference. The ANOVA itself does not tell you where the difference is. It just tells you there is a difference among the groups. You have to do a post hoc test to figure out where the difference is. So we have different types of ANOVAs. We have the one-way ANOVA, repeated measures ANOVA, and factorial ANOVA. Wow. So this is a mouthful. This is an example of ANOVA results, right? And I'm going to break it down. So first of all, in yellow, that tells you the type of analysis that was used. It's a one-way between subjects ANOVA. So that right there, you know that there are two different groups, right? In green, the effect of sugar on memory for words in sugar, a little sugar, and no sugar conditions. Okay, so our independent variable is sugar. The levels are a little sugar, and in sugar, a little sugar, and no sugar. So there are three conditions. And the dependent variable would be the memory for words. F2, 12 equals 4.94. P equals 0.0027. So F tells you it was an ANOVA. It's the F statistic, right? 2 and 12, that tells you the degrees of freedom. And it's actually between groups and within groups. And I'll show that explanation there. And then 4.94 is the value. And then, of course, the p-value indicates that it was significant. Look here in yellow, post-hoc comparisons using the Tukey HSD test. So that tells you the type of post-hoc test that was conducted to find out where the differences were. And here you go. It indicated the mean score for the sugar condition. So M equals 4.20, standard deviation 1.3. That's the sugar condition. Then you have the no sugar condition, the mean and standard deviation. And then you have the little sugar mean and standard deviation. We give you this data, these numbers, so that you can see yourself, are there really big difference is the means? And how about the standard deviations, right? You want to know the measure of central tendency for this group and the measure of variability. So it says a little sugar condition did not significantly differ from the sugar and no sugar conditions. So the little sugar condition is kind of the in between, right? So it has to be fairly extreme. Either you have quite a bit of sugar or no sugar at all, and then you'll see a difference. So here is the interpretation. These results suggest that high levels of sugar really do have an effect on memory for words. Specifically, our results suggest that when humans consume high levels of sugar, they remember more words. However, it should be noted that sugar levels must be high in order to see an effect. Medium sugar levels do not appear to significantly increase word memory. So I always want you to interpret results. It's important for you to demonstrate that you understand what all these numbers mean, because just giving the numbers, anybody can do that, right? It's the interpretation. That's the value you bring to the table when you look at all these numbers, right? You have to be able to put it in simple words to anybody reading what the results mean. Correlations. So correlations are, our most common statistic that we use. So when we see a correlation result, you're going to see the R. So remember, the funny looking X is chi-squared. T is for t-test. The F is for ANOVA. For a correlation, we call it Pearson's R. So you're going to see an R in the results. And then the number in parentheses, that's the degrees of freedom. So for correlations, the degrees of freedom would be N minus 2. So if you want to know how many people or how many observations are involved, add 2 to whatever number is in that parentheses. So you have R degrees of freedom equals your value for the R statistic, and it's going to be anywhere between 0 and 1. And then you have the p-value. So for example, results of the Pearson correlation indicated there was a significant positive association between transformational leadership and job satisfaction. R there tells us it's the R that a correlation is happening. 112. So 112 is our degrees of freedom. Plus 2 gives us our sample size, or the number of observations. So it's 114. P equals, so the R statistics 0.6, and P equals 0.012, which means it's significant. Here's another example. IQ and GPA were found to be moderately positively correlated. You have the R 38 again. So how many people are involved? 40 equals 0.34, positive correlation, right? And then P equals 0.032, which is less than 0.05. So it is a significant result. And then the last one, among students of Hogwarts University, the number of hours playing Fortnite per week and midterm exam results were negatively correlated. So there were 80 people involved, right? 78 plus 2 equals negative 0.45. So it's moderately negatively correlated. And P equals less than 0.001. So that means, very high confidence that this did not happen by chance. And so here in this, I just kind of highlighted R indicates the analysis used. 112 is the degrees of freedom. And then you have your p-value, which indicates if it's a significant difference or not. Remember, significant difference indicates whether or not we believe that the results happened by chance. If it's significant, less than 0.05, then we believe that we got the result because that if we repeated the study multiple times, that we would get these results over and over again if it's less than 0.05. So confidence intervals are another way that we convey, where do we think the population parameter actually lies? So with a sample statistic, right, you get a range in a confidence interval. It's an interval, so you have a range of numbers. If you have a wide confidence interval, well, you have, increased confidence is going to happen, but your precision is terrible. It's sort of like when you look at the weather report and it says, well, the weather today is going to be anywhere from 60 to 80 degrees with high confidence. Well, that's great, but that's a 20-degree difference. It's not really helpful, right? So you don't want to have a really wide confidence. You don't want a really wide confidence interval. You want it to be narrow but precise. So large standard of error, large interval. And it gives you an indication of the effect size. So the wider the range of numbers in your interval, it tells you that the effect size is probably pretty small. If it's a narrow confidence interval, then the effect size is pretty big. So here's an example of a result with a confidence interval. Participants who heard one Kanye West song on repeat for 180 minutes reported no less anxiety than those who heard one Mozart movement on repeat for 180 minutes. So here you have, R squared equals 0.22. F value is 132 equals 7.33. Excuse me, P equals 0.052. So no significant difference. There's the confidence interval 0.11 and 1.23. And then our hypothesis that the genre difference would influence anxiety levels was rejected. So every so often in results, and we are encouraged to use confidence intervals, you'll see that CI, that stands for confidence interval, and then you'll see the range of values. So let us recap the different research strategies, right? So you have descriptive, correlational, experimental, quasi-experimental, non-experimental. When we have descriptive research, what we're asking is, what is the current state of individual variables? What variables are even included in this phenomenon that we're studying? So for example, how much does an average adult sleep? With descriptive research, we're usually just looking at one group. We're only looking at one variable measurement, and the goal is just a snapshot description of what's happening in a population. In descriptive research, we are not looking at if there's a relationship between variables. We're just describing variables that exist in one group. With correlational research, so descriptive research usually happens when it's a new phenomenon. I'm not really sure of what's going on, so let's describe what's going on. In correlational research, now we know the variables and we want to know how are they related to each other. Is there a predictable association between the two? Is there systematic, predictable movement between the variables? So with correlational research, we're usually looking at one group and we're looking at least two variables measured for each individual. We want to know if if changes in one variable are consistently and predictably associated with changes in another. Remember, correlations would be linear, could be curvilinear, could be positive or negative. In quasi-experimental, experimental, and non-experimental research, if we're looking at two or more groups, then we're looking at measures on the same variable, and then we're comparing group means. So when we want to determine which statistic we're going to use, we have to think about these 4 criteria. What is your research question? How many groups are involved? How many variables are involved? And what is the type of data you're collecting, your scale of measurement? Is it qualitative, meaning nominal and ordinal, or is it quantitative, interval and ratio? So what I did is I pulled together these tables to give you a sense of, guide you, right? If you have one group with only one score per participant, this is what you could do in terms of descriptive statistics. If they're numerical interval ratio, you can look at the mean and standard deviation. You can also look at proportions or percentages to describe across categories. In terms of inferential statistics, you could use a single sample t-test, or you could use a chi-square test for goodness of fit. Right? You could see how much does our sample really replicate what's going on in the population proportion. If you have ordinal scores, then all you could really do is the median, right? You could also get proportions or percentages to describe what's going on. Like the median would describe what's going on across your categories. The only inferential statistic you could use is a chi-square. Again, it's kind of looking at the comparison of population proportions. And with nominal scores, remember, those are just categorical, completely devoid of any kind of ranking. They're just different. All you can do in terms of descriptive statistics is the mode. And so I did this. So that's for one group, one score. You have here, if you have one group with two variables, and then here two or more variables. So I broke this down. Really, this is going to help you when you transfer so that you know what kind of statistics that you need to use. And so I do encourage you to take a good look at these tables and have an understanding and why I, really harped on what scale of measurement will you be using in terms of collecting your data, because it really impacts what kind of analysis you can do. Right, so if you are comparing two groups on one independent variable, right, the z-test you could use, but you have to know the population variance. So most of the time, we're not going to know the population variance. So what we would do is we would go to the two-sample t-test, right? So the question we would have is, based on the sample from each, are the two population means different? So with a t-test, it can be any sample size. You don't need to know what's going on in the population. The within group comparison would be the dependent samples or paired samples t-test, right? So what we're asking here is the mean on the pre-test significantly different from the mean on the post-test? Again, any sample size, we are comparing one group to themselves. Don't need population information. And with the independent group t-test, we're looking if two groups are significantly different. We would specify the null and research hypothesis, talk about the alpha level, calculate degrees of freedom, and calculate and consult the table. Those are the steps to the independent groups t-test. And we will go over that so that you can do it. Fun, 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 right? So, for example, question is, does hypnosis improve reading retention? So the null hypothesis, remember, that's saying that there is no difference. The observed difference between sample groups is due to chance. In other words, the intervention of hypnosis is not working. The alternative hypothesis is the observed difference between sample groups reflects a true difference in the population. The independent variable had an effect, and then the alpha level, again, standard is p equals 0.05. So this is an example of the t-distribution, which looks a lot like the normal distribution, but in terms of characteristics, you could see that the values are different from a normal distribution. So the probability of all possible t-values would follow this distribution, and I will give you the table that you're going to see, the t-table in terms of the values, because you need to calculate the t-statistic, the t-value that you're going to compare your t-statistic to. So here is the formula for a t-test. What we're looking at is the group difference, so the difference between the group means, right? As the t-value increases, right, that means the difference between the group means is very big. And then you divide it by the within group variability, which is a value I would give you. So if we had, that example about the hypnosis group, control group, and we had a sample of 20, which is really small. Let's say the hypnosis group mean was 22 and the control group, the mean was 15, and the standard error of difference, which I will give you, is 0.79. You would subtract 15 from 22 and divide by 0.79, so your t-value is 8.0. 0.86. Okay, so now we want to know, is this significant? First of all, we have to calculate the degrees of freedom. So the degrees of freedom is n, to the number of participants or observations, minus the number of groups. We said the n was 20, subtract 2, because we had 2 groups, hypnosis group, control group, so our degrees of freedom is 18. If the hypothesis specified a direction, then you use a one-tailed t-test. If they did not specify direction, we just said there's going to be a difference. So specifying a direction means one will be greater than the other, right? Then if you know what you're testing for, then it's a one-tailed difference. If you're just saying there's going to be a difference, we don't know which way it's going to go, then you have to use a two-tailed test. So most researchers do use a two-tailed test. So once you know the degrees of freedom, the what kind of test you're doing, two-tailed or one-tailed, and you have your alpha level, your p-value, then you can look at the table. So here is a table that I would have you look at, the critical values of t. So if you look at the top, it says significance level. And then either we're looking to look at the one-tailed or the two-tailed, right? P equals 0.05, we're going to look at the two-tailed one, and the degrees of freedom is 18. So there, you see that the two-tailed one, 0.05, the arrow is pointing to it. So we're going to look in that column. And then we look for the degrees of freedom. There's 18. And we look for the intersection of the row of the degrees of freedom and the column of the significance. And we have the t-value of plus or minus negative 2.1, sorry, plus or minus 2.101. So what you would do is you would maybe draw out the t-value, and then you would mark off negative 2.101 and positive 2.101. What you want to know is, does your t-value fall outside of that range of plus or minus 2.101? Our t-value is 8.86, so that means our value is greater than the 2.101, that critical value, so we can reject the null hypothesis. Means that the means are significantly different. How would you interpret it? The hypnosis group has significantly greater reading retention than the control group. So you should be able to take these steps and conduct a t-test, right? It's actually not that hard. I will give you the standard error of difference. So what you need to know is what to use from it. So let's take a look again. Here we go. The example. I will give you how many people are involved, right? I'll describe it somehow. So we had 20, 10 per group. We have the mean, and that gives you standard deviations. And you can calculate your critical value. I mean, that's your t-value. Then you have to find out your critical value. So your t-value is the calculation you have for the difference of the group means divided by the standard error of difference. So you will be provided that kind of information. You have to figure out what the critical value is, right? The critical value, all you need to know is the degrees of freedom. So look at the n minus the number of groups. Determined from the information given, was there a direction specified? Was the alternative hypothesis specific in terms of which one would be greater or less? If it was not, then you assume a two-tailed test. And then if I didn't say anything else, then your p-value, it should be 0.05. So the key is you need to know which table, which column and row to look at for your critical values, right? 0.05, two-tailed. The degrees of freedom, there's your critical value. You would have a line plus or minus, so minus 2.1 plus 2.1. And does your value fall outside of that range, plus or minus 2.01, 2.101? It does. If it does, then you know it's greater, that it's greater than the critical value. You can reject null. And then you interpret your results. So that's what I would expect in terms of conducting a t-test. remember that you use the ANOVA if you are comparing 3 or more groups, right? T-test is only for two groups or two types of observations. Remember, it could be one group repeated measures or one group compared to the population. For the sake of this class, we're just going to do the between groups, the independent samples t-test calculation. ANOVA, remember, is the group difference. We're looking at the between group variance divided by the within group variance. And you're just figuring out, is that due to chance or random error? Remember, as I mentioned before, the F statistic only tells you if there's a difference, yes or no. It doesn't tell you where there's the difference. And that's where you would do the post hoc test. And here's just an example of that result. So when you have a factorial design, you're going to be doing a multi-factor ANOVA in terms of analysis, right? So this is, remember, I kind of showed you a table before, and the idea is like, okay, is there a main effect? Is there an interaction? Well, you have to actually use inferential statistics, the ANOVA, to find out if those differences are significant. So when we first talked about factorial design, I did not talk about significance of the results. I just said there is a difference. But the truth is, when you're doing the research, you actually do have to conduct inferential statistics to determine if the difference is significant. So in terms of interpreting F, let's give you an example. 3 professors were each teaching one section of a course. They all gave the same final exam. They want to know if there are any differences between their section scores. So they reported that F 2, comment 242 equals 1.07, P equals 0.35. So I could give you a very simple scenario like this and ask you 2 questions. What are the null and alternative hypotheses? And what is your decision, right? Regarding the null hypothesis, and state your conclusion. So what would I look at? Well, based on these results, right, P equals 0.35. So the null and alternative hypothesis, there's no difference in scores among the sections. There is a difference scores among the sections. Make a decision regarding the null hypothesis and state your conclusion. There is no significant difference among section scores. We failed to reject the null hypothesis. And then I should have added this, and this is what I would want from you, is that there were the professors, there was no difference in terms of the section scores among the 3 professors. So that is it. Let me go ahead and stop this. Whoops. Okay. So let me end the recording. Do you have any